Hello, I'm Mr. Craig, and I wish to go over the answers to the practice for the first quiz. So let's take a look at number one. Number one says, write the correct complete electron configuration using notation, examples like 1s, 2s, all that jazz, for the following atoms. So the first thing you need to do is be able to find the element, and I'm going to give you a periodic table for the quiz tomorrow so that you can do the electron configurations. But while you're doing the practice, go ahead and use the periodic tables that are around the room, or use the one that's in the back of your book. So go to your periodic table, and the first one was nitrogen. So nitrogen's located right here. So don't forget that when you're looking at doing electron configurations, the s orbitals are located here, and the p orbitals are located here. Now the nice thing is, we rarely will get into the d orbitals, which are down here. But remember that the energy level is the same as the row that the element is within, except for the d orbitals, it's one less than the row they're in. So when you get into the d orbitals here, this is actually in the fourth row, but it's one less. So these are the three d's. And we'll never get into the f's because, again, our focus for organic really lies right in this area here with hydrogen. Okay, so with the s and p orbitals, it's very nice because the s starts off with the first energy level, the p's start off in the second energy level, and it happens to be in the same row. So again, when looking at it, nitrogen's located here. So first row can only have an s orbital because there's only one possibility for orbitals, and recall back from honors chemistry why that is. So it'll go 1s, and each of those boxes represent an electron, so 1s2. And then you go to the second row, now you're in the second energy level, so 2s2. And then once we leave the s orbitals, we're now in the p orbitals, and then we count 1, 2, 3. So the electron configuration for nitrogen should be 1s2. And then once you fill up the first energy level, go to the second energy level. Now we go to the second energy level. Always start all your configurations in the s orbital. And again, it's two of them. So 2s2. And then from there, now we're in the p's. So still second row, so 2p3. Just that easy. Okay, the next one is argon. So again, let me move that up, sorry. So argon, in this case, is located, I can't move that guy. Okay, argon is located right here. Oops, sorry. Argon's located right there. It's in the third row, but it happens to fill up all the orbitals up to argon. So in this case, same thing. Going to start off every energy level in the 1s orbital, so we'll fill up the 1s, first row, then we go to the second row. So 2s2, okay, then we move on to the two p's, and there's 1, 2, 3, 4, 5, 6 of those. So 2p6, and then once you fill up the second row, go to the third row. So we start off every energy level with an s orbital, so that's 3s. And we're going to drop 2 electrons in there, and then move over to the p's. And since we are still in the third row, keep it in the third row for these p orbitals. So 3p6. 3p6 because, again, there are 1, 2, 3, 4, 5, 6 elements in there. Okay? All right, looking at number 2, says determine the likely or most likely formula for the following molecule. So here in this case we have CH question mark and then oxygen. Now probably one of the better ways to solve this is to draw the Lewis structure. And by drawing the Lewis structure, make sure that you're actually indicating how many electrons are in the Lewis structure. So carbon, when you look at carbon, carbon has 4 valence electrons because it's in group 4. So there's 1 carbon with 4 electrons. Hydrogen, we'll skip that for a second. So something. And then we have oxygen, and oxygen is in group 6A, so that means it has 6 valence electrons. And there's only 1 of those. So the question's asking, how many hydrogens should we have? Well, at this point right now, we have 4 plus 6, which is 10 electrons. Keep in mind, whenever you're drawing Lewis structures, you always want an even number of electrons. So putting a 1 there would give us an odd number. Putting a 3 there would give us an odd number. So, but putting a 2 there, that gives us an even number. And if you've had AP Chemistry and formal charges, and you don't need to know formal charges for this, but I'll give you the little Cliff Notes version of what formal charges deal with. When we're looking at these elements over here as external atoms, these elements right here want to have a single bond. Okay, so a single bond as an external atom, or one bond, let's just say that. When you're looking at these elements, these nonmetals, they want to have a double bond as an external atom, or a total of 2 bonds. So what that means is, for the group 7, they want to have 1 bonded pair, 3 lone pairs. This element wants to have 2 bonded pairs and 2 lone pairs. If I look at this one, or the nonmetals, really nitrogen and phosphorus, they want to have a triple bond as an external atom, or 3 bonded pairs and 1 lone pair. So when we come over and look at the oxygen, this looks great because, number 1, we have an even number of electrons. When we draw this shape out, and I would suggest you draw this out, so we have carbon and a hydrogen. So we have our 2 hydrogens, as we would suggest. And then when you look at the oxygen, it's an external atom. Just like what we said over here, that oxygen, sulfur, and selenium, when they're external atoms, they want to have a double bond, or 2 bonds. So in this case, we have a double bond, but we also have these lone pairs of electrons, which oxygen loves to have. So now, when we look at it, we have 2, 4, 6, 8, 10, and 12. Let's get that arrow out of the way. Electrons, so we can have an even pair there. So this would give us 2 as our identified how many hydrogens we want. All right, looking at this compound, this one's kind of unique because this actually gets you ready for your chains. So when we're looking at the chain here, we can look at, okay, well, we have 4 electrons from this carbon, 4 electrons from that one, 4 and 4. From the hydrogen, we have 1 electron, but we have 3 of those, plus we have 2 of those, plus we have 3 more. So that gives a total of, let's see, 8 electrons from these carbons here. And up here we have 4 times 4, which is 16, so we have 16 plus 8, which has given us an even number of electrons. So keeping in mind that when you're drawing Lewis structures, you want an even number of electrons. So bad numbers for this one, 1 and 3, these are bad numbers. So your best option is a 2. And when you draw this out, what you're going to have is, oops, when you draw this out, you'll have your carbon. So there's our CH3. Then we have our carbon with our 2 hydrogens. Sorry about that. So there's our CH2. And then if we go with the 2 hydrogens as proposed here, then that gives us our 2 there. And then the last one. And when we look at this, all the carbons have 4 bonds. So we have 3 bonded hydrogen here, and a carbon's bonded to it, and so on and so forth. Okay? So the best option for this one is 2. Keeping in mind, Lewis structures, especially for organic chemistry, want to have an even number of electrons when you draw the Lewis structure. All right, number 3, draw the correct Lewis structure for the compound, and then draw the line, wedge, dash structure for the following. Okay, so here we have CH3O, CH3. First thing you want to do is find out how many electrons you have. So I have 2 carbons, which each carbon brings 4 electrons. Again, from here, they're valence electrons. And then I have an oxygen, which is 6 electrons. Again, from the periodic table, there's 6. And then I have the same thing with the other carbon here. I'm sorry, the carbons are already accounted for. And then I have my 6 hydrogen, and each hydrogen brings 1 electron. Remember, hydrogen wants to have 2 electrons, but it only brings 1 for each. So that gives us a total of 6 plus 6, which is 12, plus 8, which is 20 electrons. So again, when drawing this out, put your carbon here, get your hydrogens. Oxygen's next, and then put your other carbon and hydrogen there. Now, at this point here, we have 2, 4, 6, 8, 10, 12, 14, 16 electrons. So there's 18. Oops. There's 20. So what's nice, again, even though oxygen technically is not an external atom, it still has its 2 bonds and its 2 lone pairs. That's what oxygen likes to have. Okay? And then the last question here. It says, indicate the hybridization and bond angle for the molecule in question 3. Hint, only use the central atoms that can exhibit hybridization. You do not need to draw the structure again since you already have it. So the hybridization for this, so looking here, let's look at this. So looking at this carbon, we have hydrogen, hydrogen, and oxygen. So we have 4 elements on there. So this one has sp3 hybridization. And again, it has a tetrahedral shape, and probably the easiest way to remember how the type of hybridization is, look at the central atom. However many external atoms or lone pairs are on there, that's how many letters you should have. So we have 1, 2, 3, 4 external atoms for this carbon, therefore we have 4 letters. Looking at the oxygen, we have a lone pair, carbon, another lone pair, carbon, and we go back, we have the same thing. We have sp3 hybridization on the oxygen as well. Because we could, technically, we could stick another atom there, or 2 atoms in there. Okay? And then the last one, looking at this carbon, we have a hydrogen, an oxygen, another hydrogen, and it also has sp3 hybridization. Now, it is possible to have different hybridizations on a molecule, so this is what you want to do, and I know for sure that we have different hybridizations in the homework. So if you should happen to have different, note the differences, but if they're all sp3, then just write sp3. If there's more than one type of hybridization, then put your comma and write the other one as well. And lastly, the bond angle. So the bond angles for sp3 is 109.5, but I'll accept 109. And then sp2, that is 120. And sp, that's our linear shape, that's 180. Okay, so in this case, since they're all sp3s, we're going to say that the bond angle is 109, and if you want to say 109.5, that's fine. Hope this video helped.